All right, so the question was from Sapling regarding is that the right substrate?
There's one more hydrogen coming off that carbon next to the bromo.
So I'll put the hydrogen in just to keep track. So the reaction, when you look at this, they're asking you basically to predict the product, but to understand how to do that, you really want to understand the mechanism. So when you look at this, what's the classification of that bromide? So it's a secondary, and I'm gonna just do that in red here. So secondaries are on the borderline with reacting via SN2 or SN1. And so that's sort of like one of the things you have to distinguish. Yes?
So how could you say that there was secondary?
So when you look at the carbon bearing the leading group, in this case the bromine, that carbon has 1, 2 carbons. So yeah, one of the things when I ask like what's the classification, that's going to help you determine by which mechanism it occurs. So the secondaries are sort of on the borderline defense, which can make it hard. So what do you need to do then? You look at, so the laser thingy here. When you look at what you're reacting with, you have water and isopropanol. So neither of those has a metal with an anion, right? So they're not strong nucleophiles. So under these conditions, with a secondary substrate and in neutral molecules, it's going to go SN1. So that means the bromine's going to ionize. And when that happens, based on today's discussion, when that bromine ionizes, what's the classification of the carbocation that forms? Yeah, it's still secondary. So that bromine's going to leave. That's the first step of this mechanism.
Carbon gets a positive charge.
Yes. So then you have your, I'll just draw the bromide. That's the counter ion. So again, this is the rate determining step for an SN1, and so it's called ionization. You're forming a secondary carbocation. And again, when you get to this stage, this is where your sort of your gate is. You have to examine the carbons next to that to determine if a rearrangement can occur. So I'm going to say the carbon bearing the carbocation is the alpha carbon. We have a beta carbon, and I'm going to call it beta prime because they're different. So this carbon here that I'm sort of hovering over with the laser, that carbon has 2 hydrogens. It also has another carbon-carbon bond. This beta prime has a hydrogen and a methyl group. So this is where it sort of gets a little tricky. We know that if you start with a secondary, the only thing it can do is go to a tertiary. If something from this carbon moves over, like a hydrogen moves over, you're forming another secondary. So it doesn't want to do that. But this carbon has 1, 2, 3 carbons. So this hydrogen can move over, meaning that the charge then goes there. So when that happens, you form what type of carbocation? You form a tertiary carbocation.
Because the carbon is 3 other carbons, but then
Yeah, so mechanistically, this hydrogen at the beta prime carbon will migrate over. In doing so, that plus charge has to go over. So again, this is a one-way arrow. It's irreversible because you're going to something that's more stable.
So you chose the carbon that had the most carbon connected to it?
Yes, exactly. So now that has 2 hydrogens. That has the methyl group. There's the carbocation. There's the bromide counterion. So now we're at tertiary carbocation, and this does not have the opportunity to rearrange anymore. So because they're specifying that the reactions run with this organic solvent, what I'm going to write next is the isopropanol actually trapping that carbocation. So in this case, it's a neutral nucleophile. So it's neutral. These electrons form oxygen-carbon bond, and that plus charge migrates onto the oxygen. So let's draw that out. So I'm no longer going to put those explicit hydrogens in. We've balanced the charge, and then to get, yeah.
So the OH that you drew above the tertiary, that came from.
It's coming from this. So again, I'll do my best to specify what is solvent and what is the nucleophile so that there's no ambiguity about it. And so what I'm going to do next is just have a proton transfer. Just do water to do that. And then this is going to result in what we'll claim is the final product. So whether sapling accepts that, or alternatively, instead of having the isopropanol attack, it may have water attack. So instead of ending up with an ether, you would end up with an alcohol. I'm not sure what it's going to accept as correct.
So where did the other 2 carbons, or 3 carbons come from? That's attached to the oxygen.
So this molecule here, I'll draw it in. I'll draw it in red. So this molecule, isopropanol, looks like that. So I haven't really used that nomenclature a lot in class, like what this I means. PR is propyl. So the I is basically, it means it's secondary propyl, but the abbreviation is I, iso meaning same. So like these 2 methyl groups are the same, so that's how they get isopropyl.
Pro and the PR, where did they go?
So this is a representation of that.
Oh.
So it's converting like the shorthand notation into a chemical formula.
So where did you use the H3O?
So that came from using this last step is what I called in class as a proton transfer. The reason this last step is important is because like the chemicals you guys use in lab, they don't really exist with charges on them. Like if you're measuring something out, like this doesn't exist. What you have to end up with is something neutral. And so the proton transfer is important to do that. And so water is acting as the base, and then it's abstracting this proton here. And when you cleave that bond, oxygen then gets its two lone pairs to remain neutral in the product.
I was trying to use the H2O. I wasn't trying to use isopropyl. I thought that was just a solvent.
Yeah, again, I don't know all these sapling problems, so I don't know if it's going to accept that as right. Next question. You want to do SN2? So I'm just going to pick some out of this book here. So I'll put a reaction down and then we'll go through the mechanism. So we're taking this compound, which is an ester. We're treating it with lithium iodide in DMF, which is a solvent. So this is a polar aprotic solvent. One thing I didn't mention on the prior problem, for SN1, you have a polar protic solvent. So even though we didn't get a lot of time to spend on this material like in class, we'll keep reviewing it as the semester goes on, and you'll get a little bit more familiar with these solvents. So the product that they're showing is the following. So you're ending up with this species here, which I'm going to call a lithium carboxylate and ethyl iodide. So what we want to do is understand the mechanism by which this occurs.
Could you say what the difference is between protic and aprotic?
Sure. I'll make a little box down at the bottom here. So in general, solvents for substitution. So SN2, you want polar aprotic. For SN1, you want polar protic. The polar protic is probably a little bit easier to understand. So what are some examples of that? So like water, methanol, ethanol, isopropanol. So the polar is sort of straightforward to understand. It's anything that has it's a dipole moment. So a covalent bond that's polarized based on electronegativity. The protic means something like OH or NH. More often than not, just to make your life easier, just think of any sort of alcohol is typically what these are run in. So polar aprotic, these are ones which you're probably not as familiar with yet. They still have dipole moments, but there's no, what I want to say, acidic proton. So let me just, I'll put the abbreviations, and then I'll actually draw out the solvents so you can see. So the one above was DMF. We saw in class DMSO. Acetone is a good one. Acetonitrile. So what exactly are these? So I'll draw those out. So structures. Of polar aprotic solvents. So there's DMF. That stands for dimethyl form amide. So the functional group there is an amide. DMSO. That stands for dimethyl sulfoxide. Acetone is 2-propanone. So that's a ketone. ACN is acetonitrile. Let me, I'll draw that out so you see what that is. So there it is, acetonitrile. So these are all polar molecules, but they don't have like an OH or an NH bond in them. And again, the reason that both of these substitutions use polar solvents, if you remember, the reaction proceeds through a transition state that's developing some sort of charge. The solvent stabilizes that charge. So as we stated in class today, if you look at what you're starting with, we're starting with an ester. We're ending up with ethyl iodide and a carboxylate. So what is really changing, if you could verbalize from the starting material to the product? So name something that's changing here and something that's forming over there. Or yeah.
Like a bond that's attached to the oxygen, it's going to be associated.
So if you'll permit me, what I'm going to do in maybe green here, this bond is cleaving. So in our mechanism, we have to show an arrow that cleaves that bond. So in the product, the oxygen ends up with 3 lone pairs, and it starts with 2, right? So that oxygen's getting a lone pair, and then it has a negative charge, and it has a lithium counterion. So what about this carbon right here? What's happening to it?
It's attaching to iodine.
So it's forming a bond to iodine. So sort of write that. So now with that knowledge, that's what we have to depict with these curved arrows. I'm just going to redraw it again, just so it's not as cluttered. So of the two things that I just drew, what's the nucleophile and what's the electrophile? The iodine's the nucleophile.
And the lithium is the,
Well, the lithium's the counterion.
oh.
So if this is the nucleophile, then this is the electrophile. So it's not, don't overthink these things. How you classify it is, for like an SN2, this sort of species is going to be the nucleophile. You have a metal cation and then some sort of anion. That anion is supplying the electrons. That's the definition of a nucleophile. So you originally said base. The distinction between the two, the way you want to think of it, in this case it's acting as a nucleophile because it's forming a bond to carbon. If it were abstracting a hydrogen, then we would call it a base. So a nucleophile will always react with an electrophile.
I thought if you think about it in like a Lewis acid definition, it basically what's supplying the electron.
Yeah, it is. So it is a Lewis base.
Okay.
And then this is a Lewis acid. Because that carbon is accepting those electrons. But I think in a more broad sense, thinking of it as nucleophile, electrophile is a bit more appropriate. Yes?
You said the electrophile would be the oxygen.
It's the carbon. So let me draw in how we think about that. So because this oxygen has two lone pairs, I'm going to call that delta minus. The carbon bonded to it is therefore delta plus. And we know that the iodine is supplying the electrons, which is negative. So it's attracted to the thing that's positive. And the arrow is going to flow this way. So that arrow is showing you how this bond right here is formed in the product. That's the bond you just formed. And we've already said we have to cleave the CO bond. We do that. And then oxygen gets that third lone pair of electrons, ends up being negative. So that's going to be the SN2 reaction. So one thing you want to keep in mind for SN2 The-
Why you put it like plus lithium?
The lithium's just sort of like a spectator. Right now, that plus charge is balancing out this minus charge. When this attacks that carbon, this oxygen now gets the negative charge. So the lithium's just the counter ion to it. So remember, like I said, if you went into lab, you couldn't just weigh that out, like carboxylate minus. There has to be some sort of positive ion balancing it out. So now that we've run through that, let's go through a couple more examples a little bit faster. See if we can predict the product now that we know the mechanism. So in terms of like our exam review, like we're doing now, you would have to actually like write down what you think the product is rather than given A, B, C, or D and choosing the right product. So let's look at this example. Huh.
That's not a double bond, that's like projected.
Yeah, it's coming out towards you. So we want to predict what the product of this is going to be. So sodium cyanide is the nucleophile, DMF is the solvent, and then what classification of bromide are we starting with? So we have secondary bromide. We have a good nucleophile. We have a polar aprotic solvent.
If you don't mind me asking,
Yeah.
can you say how you know that the bromide was secondary?
So the first thing when you look at this substrate, you're going to identify this is a heteroatom, so it's not carbon, it's not oxygen, or it's not hydrogen. So this carbon-bromine bond, that's going to be the best leaving group in this molecule. Yeah, so you're looking at the carbon bearing that leaving group, and then you're basically counting how many carbons are bonded to it. So we have delta minus, delta plus. Again, the sodium is the counterion that's balancing out any negative charge. The cyanide is the nucleophile. It's going to attack the carbon bearing the leaving group. So let me draw. I'm going to draw it in a way, and then I'm going to ask you a question just so that we're all on the same page. I'm going to draw the carbon backbone the exact same. I'm not going to do any rotations, any twists, turns, whatever. Let me just go ahead and put these numbers in. And these are numbers not related necessarily to how you would name the compound. It's just strictly for tracking the atoms themselves. So we know at carbon 2, that's bearing the leaving group. That carbon's being attacked by cyanide anion. So when I draw that CN group in, do I draw it as a wedge, which is coming out towards you, or a dash, which is going away from you?
A dash. It's like it's inverted when it comes in from the other direction, right?
Does everyone understand that? So it's going to be drawn as a dash, which is away from you, because the nucleophile has to attack 180 degrees from the leaving group.
Oh, yeah.
So that's pretty important to realize with substitution reactions. So we're going to draw that with the dash going back. And so that's how we understand that an inversion occurred. So here's another sort of tip. For SN2, inversion will happen with stereogenic carbon. So just so we get a little practice, what's the R or S designation of carbon 2 in the starting material? So carbon 2 in the starting material, what would you assign to that, R or S?
R.
I agree with R.
I'm kind of split.
1 and 3 are both carbons. So how do we differentiate them?
What's attached to those carbons?
So what, you have to sort of go out to the next thing. This only has hydrogens, and this has an oxygen. So that's going to be the second priority. So you have 1, 2, 3, the hydrogen's back. So we're going clockwise, so it's R. And then what would you assign carbon 2 in the product as?
X. No, I think it'll be the same way as one.
The same as what?
It'll be
Same
R.
as the other one, I think it'll be R.
You think it'd be R?
I think it's best because in that one, the hydrogen's coming towards you. You have to put the lowest priority to the back. So doing that would switch it from
R to S.
So let's walk through it. Of these, what gets, now carbon 2 in the product, what gets the highest priority and why?
Maybe
Nitrogen.
I think CN would get the
I mean, no, maybe I wouldn't think CN would get it, because isn't it just a regular CN woman?
So,
No, I might just put it in.
No,
I really don't know.
this one would, because
I
if you
think
added
it's
all that one's got a whole nother carbon and an oxygen. That's gonna be more than just the nitrogen.
I'm saying maybe like the mid-thing.
so that's what CN is.
Oh, but because it's a triple bond, you count the nitrogen 3 times. So I guess that one would.
We really don't know. We really don't
I
know.
gotta say, my confidence in answering this one is definitely not 100%. Because all 3 of those groups are carbon now, right?
Yeah.
And so obviously the methyl group is going to take the third priority of them. So you're going out to carbon. The nitrogen triple bond you can view as nitrogen, nitrogen, nitrogen. But still, if you look up there, that has an atomic number of 7. If you go out to oxygen, that's 8. So I'm inclined to think that that group is going to get priority, even though
That's what I would do too, but oxygen would
so
be
this
priority.
this one is definitely, there's a bit of a nuance to this. So the issue, what I honestly don't know, is that this has 2 hydrogens, right? So those are obviously lower priority than 2 of these nitrogens. But that one oxygen takes priority over one of those nitrogens. So this one, I'm not sure. So I'll be sure to ask it on the exam. I'm just kidding. I don't know. I'd have to plug it into a software thing and see what it spits out. Then I could rationalize what the correct answer is. I don't know.
I have to get used to assigning priorities quicker.
So, yeah, this one's a little tough.
So what you said, that's gonna be an R.
Yeah, because if you assign that as first priority, if you went 1, 2, 3, it's going counterclockwise, but that's towards you. So you would reverse it to get R. But I don't know.
In terms of the priorities, if it's just H, it's gonna come last, right?
Yeah.
If there's 2 H's on there and there's nothing else like an oxygen, it's like the second. Methyl, like, and then it goes like oxygen, usually obviously is poly.
I think it's like CNOL.
Makes sense.
Yeah, it's, so there's one up here. So like seen off is,
No, I think the honk,
like,
see, but, like, husband,
oh, okay, sure.
What?
Oh.
It's in
I-
the textbook.
I guess I think of it the other way.
Yeah.
It's good to know that different people think
Yeah.
differently.
Because, well, I remember Hulk because that tells you how many bonds, like hydrogen is 1, oxygen is 2, nitrogen is 3, carbon is 4.
Yeah?
Where are you coming from?
She's coming like,
H-O-C.
she's doing like back around this way.
I like.
So the hydrogen 1, oxygen 2, nitrogen 3, carbon 4. So H-O-N-C.
Oh.
Yeah.
Never thought of it that way, but
Me either.
it makes
It's an
sense.
easy way to remember how many bonds it usually has.
Yeah?
And so if two of them are the same that's attached to the central carbon that we're looking at, then you look farther out and see what it is.
Yeah, you have to keep going out. So this one, unbeknownst to me, was a little bit of a landmine that I walked into. But let's try to,
Is there anything that you feel that you should
You know, I have something.
let me just do one more of these in terms of predict the product here.
Yeah, and then say we're all done.
That was A class.
He was the hardest teacher I ever had in my life.
Me too.
So the sort of different conditions. We have a secondary chloride that's also allylic. We have a good nucleophile. We have a good solvent, polar aprotic.
When you say a good nucleophile, you mean because it has a lot of neutrons electrons.
So really, the pattern that you're looking for is a molecule that has a metal cation plus some sort of anion. The anion is what the nucleophile is. So I'm going to go ahead and number this. Again, this numbering is just strictly for keeping track of the atoms and not the name itself. So this nucleophile will attack carbon number 1, and then the azide group, N3, that's what that's called, azide, should be a dash or a wedge. So it'll be a wedge that's coming out towards you.
And can you, how would it be a wedge because of the 180?
Yeah, exactly. So maybe let me ask maybe a more straightforward question about this one. How many unique carbons would this product have?
Four.
Which 4?
2, 3, and 6 and 5 are the same, and then 1 and 4.
We got, she's rolling her sleeves up here. What's your beef?
I don't know, I really don't know.
No, you do know.
I think 2 and 3 are the same,
Why not?
because 2 is connected to the, N3. N3 is connected to just the carbon.
So what's your answer then?
I guess if there's an N4, I was like, I would count it. I'm not sure, I would say 5 then, I guess. 1, 2, 3, 4, 5. Yeah.
So we're getting there. We're not quite correct yet.
I say 30.
Is it 6?
It is 6.
If that's the case, what she explained, that would be 6.
Yeah.
Right, so in your logic, you weren't taking it exactly far enough because you were making like 2 of them somehow symmetric. If you're looking at, say, carbon 1 is your like point of reference, if you walk out here in there, 2 and 6 are definitely different, right?
Right.
1 is its own unique thing because it has this azide. If you go out to 3, 3 is definitely not the same as 2 because 2 is closer to that carbon. Even though these are CH2, 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 4 is definitely not the same as those because it's 4 away, right? So sort of look at the position of each thing relative to the other. And you can really only identify symmetry if they look the same when you go out to these positions. If that double bond were not there, then it would be 1, 2, 3, 4. So right now it's 6. So you said you had a specific question.
Yeah, still not clear on the Fischer projections and how to determine their, like, RS on those.
Okay, so we'll briefly go through that. I do have an exam that has an SN2 reaction on a Fischer projection, and it's like, I think, one of the most mentally challenging things you can do in organic chemistry.
Means coming up from fast.
I have not made this exam yet, so I don't know
Please.
what
Please, dear.
level of ferocity I'm going to use. Okay.
Are you gonna do the answer on like sheet 6 year next semester? How are you doing this semester?
And say that again in like,
Starts with water tickets. Are you gonna do this next semester in organic too?
yeah. So I only do it when class is like about your size, because otherwise it's not very manageable. So I would say of the 60, maybe like 40 of you are going to go on to Organic 2. Some people only need 1 semester. Some people are taking in the summer. So assigning R and S in a Fischer projection. So let me try to think of something relevant here. That's a crazy long bond. So this functional group is called an amino acid. So its common name is valine. And if you go on to biochemistry, amino acids are obviously always going to have this acid part. They'll always have this amine part. And how they differ is this thing here, which is called the side chain. So there's maybe like 5 classifications of amino acids. So this would be a hydrophobic side chain. So that sort of always confuses me because you're describing it by like what it does not like. Another way to describe it would be lipophilic. Do you know what lipo means?
Like lipid.
Somewhat, yeah, exactly, yeah. Like what is, like if you heard of liposuction? Yeah, so it means like fat. So lipophilic is fat loving. So what this means is there's no polar groups. It's non-polar, which means it's hydrophobic. So describing the same thing different ways. So these side you use it as a yeah. So these side chains vary amongst the amino acids, but what's common is sort of this part of the molecule. So we want to determine if that's R or S. So while you think about that, I'll draw this in another way so that we're all on the same page about what this convention means. What did you end up with?
I said yes.
Uh-oh. We have a good old-fashioned intellectual street fight here. Whose logic shall prevail?
I assigned first priority to the CO2H.
No.
It's nitrogen. Nitrogen's directly connected to the carbon.
Oh, dang it. Yeah, I was just adding them up
So,
from the
yeah.
start.
So that's a
Yeah.
pretty common thing, is to sort of like skip over one of them. But yeah, if you're looking at the atom directly bonded to it, the nitrogen gets 1, hydrogen's 4. Then between the 2 carbons, the acid has a total of 3 oxygens bonded to it. So that's 2, that's 3. So this is one of those circumstances where the lower priority group is coming towards you. So when you connect these numbers, sort of 1 to 2, 2 to 3, in that sense you're going clockwise, but since this is towards you, you have to reverse it. So what you should end up with ultimately is assigning that as S.
So can you apply that, like any Fischer projection you get like that, you can put like the wedges on the side and then the dashes on the top like that, and that's how they turn out?
So the Fischer projection, so what's sort of confusing, this like cross, this intersection, the horizon has to be drawn with wedges. The vertical has to be drawn with these dashes. That's what exactly that means.
If I can do that, I can figure it out. It's just from.
Right. So why this is sort of confusing is normally when we do these type of stereochemistry problems like this, we normally have 2 of these groups in the plane, and one is a wedge and the other is a dash. But now we're sort of moving our eyeball to a different perspective.
So, because you have to change, what do you have to change because the lowest priority is supposed to be away? You change it from R to S.
So, yeah, when you're going to get this order no matter what. So this is going 1, 2, 3. So that's clockwise, which you would assign as R. But the way that the convention is written, the lowest priority group has to be away from you. So you're gonna flip it. So if you come up with R this way, it really is S.
Right. I thought I get it when I was trying to make this. Do you flip it like where H is gonna be a dash, or do you flip it like rotation?
A dash.
What I mean by flip is not anything to do with this molecule so much. When we did this, we determined it was R. What I mean by flip is because this is towards you, you're flipping the R to S. That's what I mean by flip.
Okay, so really H is gonna be dash.
from the perspective that we're supposed to look at it, it's supposed to be a dash now because you flip it. Because it's going forward right here and this. Okay. I wish I could like, okay, act like you holding the hydrogen in your hand and you would be counting like 1, 2, 3, and that's R. But right there, the lowest priority is coming towards you. So, you know, he always said hold the lowest priority away from you. So that means that there would be a dash line. And then we change the letter from R to S.
So another way, how you just described it with your hand, you're holding that lowest priority towards you. Now, I know this can sound weird, but imagine like you can be where you are, but like part of your body rotates out this way. And now you're looking at it the other way, but you're still holding it the same way.
Yeah.
So that's how you would get the right answer.
I kind of just like, you know how on the phone you could like move it with your fingers
Yeah.
and stuff? I
Right.
just think about doing that in my head.
Yeah, so I mean that's the skill, is being able to do this, like I said, in your head without a model. That's really where the development comes.
What confuses me is when you're saying flip, but then when you do this, it's like rotation. You see what I'm saying?
Yeah, I guess maybe
And flip is like,
maybe the words that I'm using are probably not the most appropriate in terms of connecting the concepts.
so really you're rotating it from to that.
Yes. So let's do another one.
Okay.
So with Fischer projection, are the side ones gonna always be coming through?
Yeah.
Yeah, that's, so we'll do so this is a carbohydrate. It has a 4-carbon chain. So it's a tetrose. So how many stereogenic carbons do we have in here? So there's 2. They're at carbons 2 and 3. So if we number this chain, 1, 2, 3, 4. What would you assign to carbon 2? Is it R or S?
S.
What'd you say?
I didn't say anything else.
When you look at it initially, it looks like it's S. But
I did.
this is coming out towards you.
Yeah.
So you have 1, 2, 3.
Okay, why is, oh, because it's got an oxygen. See, I
So
saw
were you
it.
counting that as 1?
No, I was counting that as 3.
Oh, this is 3.
Yeah.
Yeah, so let me draw out what CHO is so that everyone knows why that's the first or the second priority.
So CHO would be first one?
It's going to be the second.
Okay.
So oxygen's 1. Now we know that hydrogen's 4. We have carbon and carbon. This carbon at the top has, you can consider it 2 bonds to oxygen and 1 bond to hydrogen. The next one has oxygen, hydrogen, carbon. So this kid's priority is 2. This one's 3. So yeah, when you do this, it's going to be R. Then what about for carbon 3? What should that be?
It's going to, in this one.
You gotta flip it.
You flip it again?
Yep, because the hydrogen
Because
comes
it's
first.
the hydrogen away. And if it's on the side in the Fischer projection, it's in the front. So if it's on Fischer projection and it's going down the sides like that, just know that you're gonna have to flip your H.
It's basically you always have to flip it.
Not always.
If in the Fischer projection and it's on the side, and it's a part of the stereogenic carbon.
I'm going to S on that second one.
I think S is the right answer. I would agree. So 3 is going to be S.
Wait,
I wish this would have clicked when I did that second one.
can you go through how 3 and 6, like with the arrow and the line?
Yeah. So I'll do this numbering in blue. This oxygen's 1. That hydrogen's 4. Now you have 2 carbons. This carbon here, which I'm putting a blue dot on, that ends up being carbon. That ends up being the second priority. And the reason that is, because carbon, what I've labeled priority 3, has 2 hydrogens and an oxygen. The second priority has oxygen, hydrogen, and another carbon. So that's going to get priority there.
Well, I have a meeting after I take, do you know what time you're gonna do the thing tomorrow for me?
I'm going to a dinner at 7 p.m., so it's most likely going to be during the day sometime. What time is good for you guys?
Not during the-
What?
I said nighttime, it'll be okay though.
I could do like, check my, I could do like 5 to 6:30.
Yeah, I can do
I think that would probably work for majority of people. I won't be able, like, I won't be able to come home, but, like, I won't be able to come home, right?
Okay, so I'll try to post it on YouTube if I do something tomorrow. Yeah, tomorrow's kind of busy.
Yeah.
Let's kind of double up the concepts here. I'll try to think of a reaction on the fly that makes sense, but will work.
So the ones that we just did, were them SN1 or SN2?
The things we just did, we were just assigning R or S. We weren't really doing a reaction or a mechanism on them. So if you're given this alkyl bromide plus sodium iodide and DMF, and you're told that a substitution is going to occur, what would the product be? How would we draw this product to be correct?
So how would you know which one you're trying to break?
So if you look at this molecule, what is the best leaving group? The bromine is. So that bond's the best leaving group. This is an ester. So the most polarized bond is going to be that CBr bond. So that's going to be the best leaving group, and you can rationalize that on, like I said, the conjugate base stability.
How are they gonna invert?
So don't let the way it's presented to you sort of like distract you in a sense. So you know that like these equal that.
Yeah.
And you know an inversion has to occur. So now if you were to draw the product in a Fischer projection, that's probably where you're getting caught up, right?
Yeah. Could you just turn it?
The thing with Fischer projections, you can do a 180-degree turn. You can't do a 90-degree turn. Maybe you can. I don't think you can. I don't think you can switch groups like that. You're allowed to do a 180-degree rotation, for sure. So think about, nothing's happening here, right?
So you could flip that.
So nothing happens with those, we just redraw them. I'm going to redraw this line, that intersection. So now what would I put on the right and what would I put on the left?
On the right, would you put iodine?
Yes.
And then on the left, you put
That was a little scary.
It's almost like you're coming over the top of a roller coaster.
I know.
You don't know what to expect.
I can't picture that one.
Yeah, it's a little.
So if you, yeah, with this it's definitely hard to sort of see, but like with, I guess let me sort of redraw this in that sense. So this is attacking opposite that bromine. That bromine leaves. So as a consequence of that, you can view this hydrogen as sort of like flipping over. And so the iodine is going to like take its place spatially.
Okay, so it's just inverting it like
Yeah, it's just like
Yeah.
on this plane.
Yeah, on that plane.
Okay, I can see that. I see it.
So you just
I
replace,
see it, it just.
you replace the legal
I
group
would've
and you
thought
just
that.
flip the projection to the other side, like kind of like a mirror image, but just
It-
replace legal.
In a way, yeah. So it is, what's tough about this is like your perspective of like, these carbons are in one plane
Yeah.
from your perspective.
Mhm. But they're actually.
If you moved your eyeball in the plane of this, they would not be in the same plane from this perspective.
Mhm.
It would be sort of like a triangle shape.
Yeah.
So it's really about how you visualize things. Did you have a question you wanted to go over?
Is there any other things that you think you need to go over for example?
So why don't we look at a radical reaction, just so we could say we covered one?
Anything
So the radical chapter was CH substitution. And what we just learned with SN2 and SN1 is substitution of some polar leaving group with another one. And so they're overall both substitution, but they're acting upon different atoms through different mechanisms. So if you're given that compound in the presence of bromine and light, which CH group is going to be substituted for bromine?
Would it be that middle one that's tertiary? Because it likes higher order carbons?
Yeah, so it's going to be the tertiary CH group.
So the one in the middle of that
Yeah.
figure, like that little ninja thing,
So this hydrogen right here.
Yeah.
the carbon.
So let's go ahead and we'll draw the product and then we'll explain how we got to it. So this H here is the one being substituted. And so how did we ultimately arrive at that? I'm going to go ahead and put all the hydrogens in this molecule, and then we're going to classify all of them. So how many unique sets of hydrogen do we have to begin with?
I'm confused because
So on that ring, dig a little deeper and don't count them all as one.
so I have a question. Where did the hydrogen come from? Because at first it was just like
So that's part of understanding whether they're explicitly drawn or not. More often than not, the CH bonds are not drawn because it's implicit that given a carbon, if you're not specifying anything else, the remaining things are going to be hydrogen. So there's going to be 5 unique sets.
and because it only had 3 other C's bonded to it, you automatically knew to put that hydrogen because carbon has 4.
Yeah. So that's what we did when we drew them all in. So there's 5 unique sets. So within those 5 sets, let's sort of resolve them a little bit. Because this is important. How many sets are sp3 and how many are sp2?
How many sets or how many?
Sets. Yeah.
This is where I always go wrong. Me and hybridization do not get along.
What'd you say? 3 for what?
3 sp3 and then 2 sp2.
So the hybridization, you're looking at,
No, backwards.
so it is backwards.
Yeah.
An sp3 hybridized carbon has only sigma bonds. An sp2 hybridized carbon has a pi bond. And an sp hybridized carbon has 2 pi bonds. So of these 5, you have 1, 2, 3, 4, 5. So these are 1, that's 2. So the sp3 has 2. The sp2 has 1, 2, 3. So we're just breaking this down, 3 sets versus, or sorry, did it as well, 2 versus 3. And the reason we want to do that for this type of problem, this versus this, which one has the stronger bond in general? sp2. The sp2 CHs are stronger. Therefore, under these conditions, they are less likely to be substituted. So we don't even have to consider them. Now we're just left with these 2. So of those, let's dig a little bit deeper. We have 2 sets that total 7 of the protons. Of those 7, how many are primary?
You just lost it.
So right now we're only looking at the 2 unique sets that are sp3 hybridized. And we want to classify them. So we want to classify the hydrogens as primary, secondary, tertiary. We said there's 3, 4, 5, 6, 7. 7 hydrogens that belong to sp3 hybridized carbon. Of those 7, how do you classify them?
We're classifying hydrogen.
Yes. How many primary, how many secondary, how many tertiary?
We have 6 primary.
So we have 6 primary. So
and one tertiary.
does everyone follow that?
Yeah, I was thinking of carbons, not hydrogens first.
So now we've drilled a little bit deeper. Now this is where we're going to make our ultimate decision of which one of these gets substituted. We've sort of already done that. And then it's going to be the tertiary hydrogen that gets substituted. But why is that? So let's look at how the mechanism of this proceeds, so that we understand why it's selective for that specific hydrogen. So again, the first thing that happens in a radical reaction is initiation. So the molecular bromine is going to cleave homolytically. So the fish hooks indicate of the 2 electrons in this bond, each bromine gets 1 electron. So we form a bromine radical, 2 bromine radicals. Step number 2 is the first propagation step. So the reason that I wanted to walk you guys through that exercise we just did is so that you understand exactly why this bromine radical is doing what it's doing. It has a choice of 5 different types of hydrogen. We said that these bonds are much stronger, so they're harder to cleave. So we're only looking at the sp3. Then of that, the reason why it's going after the tertiary, when you cleave this bond, you form what type of radical? What classification of radical?
Carbocation.
The tertiary.
So in this mechanism, we're going to form a radical, not a carbocation. But what this question is basically asking you is to go back to this. We're forming a tertiary radical versus a primary. And so the stability of the radical follows the carbocation stability. Tertiary is greater than secondary is greater than primary. And this is a special case as well because it's right next to a benzene ring and it's resonance stabilized. So this radical, which I'm going to redraw up here, abstracts that proton. It just takes practice. So now in the next propagation step, that tertiary radical reacts with the bromine. To form the product. And then most importantly, the propagating radical.
Where would you put the propagating radical in?
So see how this radical is forming a carbon-bromine bond? This bromine that leaves, that's the propagating radical, which then goes back up into this step here to abstract. Think of it as like going through the cycle again. This is another molecule that's taken through the cycle to the product. So again, overall for these radical reactions, it's important to be able to do, I think, this type of exercise first to really narrow down, okay, which hydrogen is going to be substituted. So using that sort of formal logic will definitely help you arrive at the right answer.